Can I bring up some of those
so that
citations
you can
for you?
Sure. Cherry pick
Cherry
away.
pick. There's no cherry picking. It's just simply.
Oh, you're totally going to cherry pick. We all know it. We all know you're going to cherry pick. But go ahead.
Okay, let me just pick up some of them, quickly open them for you. There's no cherry picking, but okay. Because you clearly say there's no trigonomic function for celestial navigation, correct?
No, I said there's no triangles. So try to keep it correct. There's no triangles in
so what's trigonometry?
Trigonometry is more than just triangles.
What's trigonometry?
You don't know that?
What's trigonometry?
What is trigonometry? You don't know it? Why are you trying to tell me what trigonometry is if you don't know what it is?
You're saying it's not triangles, so I want to know. What's SOHCAHTOA?
I said it's not just triangles.
Is SOHCAHTOA triangle?
SOHCAHTOA is, but there's more to trigonometry than SOHCAHTOA.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4,
it's not just solving
6.
triangles. Do you know how a fast Fourier transform works?
No, go on. Explain.
Okay, sine and cosine are used in that. No triangles at all. Do you know how discrete cosine transforms?
But you see, we're talking about celestial navigation, which specifically works with trigonomic function of SOHCAHTOA.
Well, it does. Oh, well, just show the process. Go ahead.
Let me quickly get on screen. Can I share my screen? Okay. Let's just share my screen like that. Share. Okay. You can see what's going on here? Okay, I don't need this one yet. This is just the principle of the text. I want to bring that up just now. Okay. Navigation of the stars. Okay, this is obviously different techniques. Talking about trigonometric was first used in navigation by 14th century. Several navigation techniques can be identified in navigators' personal notebooks, including the table the application of plane trigonometry. You would agree plane trigonometry requires it to be a triangle?
No.
The application of plane trigonometry. You would agree plane trigonometry requires it to be a triangle?
No.
What's plane trigonometry?
Don't know that it's not specifying it here. It's just giving a little bit of
plane trigonometry
overview.
Requires it to be on the same plane, in other words. So if I'm making an angle measurement over a plane.
Okay.
We can also use the Pythagorean theorem to find the distance between any 2 points on a Cartesian coordinate plane. Let's pick 2 points, the first with coordinates x1, y1, and the second with coordinates x2, y2. But when we draw horizontal and vertical lines through the points, you can probably see where we're going. Since the new lines are perpendicular, the triangle is a right triangle, and we can apply the Pythagorean theorem.
Well, bring up the process. Okay. Let's look at the process.
This is one, navigation by the stars.
Bring it up.
Trigonometry.
Yeah, bring it up.
One,
bring up the process that they used in that.
We're still getting there.
You're a little. Why are you scared to bring up the process that they used?
We're still getting there. Trigonometry
so
processes.
You're just cherry picking. You're proving me right by cherry picking.
Trigonometry process or celestial navigation or astronavigation subject to presentation of maths curriculum, blah, blah, blah.
Bring it up. Let's look at how it's done.
I'm just first giving all the citations showing that they do use trigonometry.
Well, just show how it's done there, Flatzoid.
Trigonometry.
Let's look at how they do it. Why don't you want to show how it's done?
Sailing with trigonometry. Okay.
Let's bring it up. Come on. Oh,
I've got it up.
Bring it up.
Trigonometry is used in navigation.
No, bring up the process. Bring up the process. Let's look at the process. And
you saying we don't use trigonometry. I'm saying we do use trigonometry. That's the argument right now.
I'm happy to go through the process in this book where there are no triangles involved. But you're saying there's triangles involved in the process, but you're not showing the process. Go ahead, show it where it's happening. You're not showing the process. Go ahead, show it where it's happening.
There's sine and
cosine. Can you show the step-by-step process of celestial navigation using triangles? Go ahead.
Let's first start with a little bit of background about lines of position in general and what they mean. When we talk about a line of position, we're just talking about some place on the earth that we know we are, or more specifically, where we were. Imagine a case in which you're floating out there on the ocean and you have a lighthouse on an island, and you want to help figure out where you are using that lighthouse. Celestially, a bearing is known as an azimuth. So we'll come back to that later. But if I use my compass and I take a bearing of that lighthouse, I could then go onto the chart and draw a line kind of backwards from the lighthouse, and I know I'm somewhere on that line. And when we do celestial navigation, we're going to do the same thing, but we're going to do it for not the lighthouses on Earth, but the lighthouses in the sky. for terrestrial or land or water, earth-based navigation would be using geometry to help figure something out. Because if you knew the height of this light, and they're always listed on the chart, and you had some tool to help you measure the angle between the bottom and the top of that light, you could create a little triangle here. And it's a right triangle. You could create a little triangle here, and it's a right triangle. It's a right angle, assuming the lighthouse is built straight, of course. So if you could measure this angle right here, call it maybe theta, that's like a mathematical angle, and you knew this angle right here, and that means you can figure out this angle right here, and if you knew the height, and you can figure out your distance using that method. So we don't often do that in navigation because we've got radar and we've got charts and we've got compasses that give us lines of position, which are easier. But this is a valid technique. And when you think about celestial navigation, we're not necessarily doing that, but the principle of triangles and angles and right angles and figuring out sides and everything is definitely helpful when it comes to a celestial site reduction process.
Can
you show the step-by-step process of celestial navigation using triangles? Go ahead.
We could do the same thing. We could set up, an angle between us, the horizon, and the sun, and it's going to turn into a big triangle that we could solve geometrically.
Can you show the step-by-step process of celestial navigation using triangles? Go ahead.
The horizon and the sun, and it's going to turn into a big triangle that we could solve geometrically. A big triangle that we could solve geometrically. A big triangle that we could solve geometrically.
Okay, you take a measurement to the celestial object, correct?
Go ahead.
An angular measurement. I'm going
You
to try to draw.
You don't need to keep.
I think
you don't have to keep asking me. Just go ahead and show the process of doing celestial navigation.
I need you to concede when I do these things. That's why I'm doing it this way.
No.
Yes, yeah. Okay. When we take an angular measurement to a star, let's say in the sky here, we are on the ocean floor or, on a ship or whatever, it doesn't matter. Using a nautical sextant, so obviously on a little boat. Okay. And we're going to take an angular reading to the star, correct? Would agree about that?
Keep going.
Okay. Now we've got two straight lines going out that way. You would agree that we have a 90 degree.
No.
We don't
That's
have
not 90. That's less than 90.
We don't have a 90.
That's not 90 there. No, that's less than 90.
That's not
maybe
90. That's not 90.
Oh, there it is. Okay, now it's 90.
We have a 90. Okay, cool.
Yeah, at that point. Yeah.
Great. And the star has a 90 as well, correct?
That's it. That's presuming. What you're doing is presuming that the Earth is flat.
That's how it's
You're
working.
making an assumption.
No,
You're making an assumption on this.
This is how the trigonometry works, mate.
Bodies whose geographic positions will be hundreds or even thousands of miles away from your own position. Theoretically, you could use the first method to plot your line of position.
So you say, but you're. This is just your claim. You're not actually showing the process of celestial navigation from a citation that you brought up. You're just inventing this process that is not based on the books that you were referencing.
I see star A, let's say, at 50 degrees above the horizon. Now, how would I get that measurement? Okay, so the way I would get that measurement is using a nautical instrument. You've probably seen it. I'm going to try to sketch it real quick. It's called a sextant. And I go to this book, and I'm saying, okay, it's 6 p.m., and I'm looking at star A. And the book would tell me, well, star A should be located at this position, okay, at 6 p.m. Okay, at 6 p.m., you should be seeing star A directly over your head, 90 degrees, right? So if I'm standing out here in the middle of the ocean at this position, okay, not where I'm at, okay, at this particular position, I would see star A directly
above my head at 90 degrees. So with those two pieces of information, okay, I can use some trigonometry. Okay, this is going to be a right angle. I have a degree here. I have a location here. Well, the only way you can do that is that you have to be a certain distance away from its location at 6 p.m. Okay, and it's basically going to build us a little circle here. So let's just make a number up. Let's say in order to see star A at 50 degrees, okay, at 6 p.m. at night, you have to be 900 miles away to be able to see that observation.
Let's say I measured an angle to the star at 50 degrees. Okay? You would agree
Okay.
that's 50 degrees. Okay, to the star.
Not to scale, that's fine.
But yeah, it's not to scale, obviously. Okay?
Yeah.
We measured 50. What's the internal sum of a triangle? 180.
180.
So that would give
Yeah.
us 40, correct?
Yeah.
Okay, so if we use the math anyway to just verify this, 90 minus the measured angle gives us the altitude, the elevation angle, which is 40, times 60 nautical miles, which gives us our distance.